lectures after the pandemic. The first time was a closed group of people because people were still afraid of COVID. This is the first time that we do an open De La Pietra lectures. And first, I would like to start by thanking the De La Pietra families, Stephen, Vincent, Barbara, and Pam, for their unwavering support over the years. You know, they've been supporting the Simons, not only the Simons Center, but also the university very generously for the last N years, where N is large. Thank you. And in fact, they fund also this series of lectures, which, as you know, you actually look, it's one of the things that you can watch in our video portal in this, when you go to the Simons Center webpage. There are excellent lectures that you can enjoy because everything is recorded with high quality. Today, you know, we had invited Elena Aprile for a long time. In fact, we've known each other since most of you were not born, I guess, at Harvard. And let me say you that, you know, Aprile is a professor of physics at Columbia University. Then after obtaining her undergraduate degree in physics in Naples, she earned her PhD at the University of Geneva. Aprile started her research on novel liquid imaging detectors under the mentorship of Carlo Rubbia, first as a student at CERN, and later as a postdoc at Harvard University. At Columbia, which she joined in 1996, she pioneered the development of a Compton telescope for gamma-ray astrophysics based on a liquid xenon time projection chamber. She later turned her attention to the dark matter question and proposed the XENON project. She's the head of the XENON project. It's very successful, and she's going to be telling us today about all these things. She has plenty of recognitions and accolades, but I think that's nice to highlight the fact that an asteroid was named after her in 2004. She has become an officer of the Italian Republic. I don't know if it's a general or colonel or... And this year she became a member of the National Academy of Sciences. So would you, Elena Aprile, thank you.
Thank you. Thank you, Luis. And I discovered that you are 1 year younger by Googling. We were at Harvard together, living next door to each other, I believe. So thank you. It's a great honor to be here. It's my first time here. It's an honor, and I am grateful to the Simons Center and to the De La Pietra family for the opportunity to give this talk today and to tell you about my research, which for the past 15 years has focused on the search for dark matter with the XENON project, with support from the National Science Foundation throughout this year. So I'll go right into that, and I have to move. Okay. So I will start with reminding us about what dark matter is. This is the dominant form of matter in the universe, and yet its nature remains a mystery. It is for near a century that the evidence has mounted that the gravitational pull necessary to keep galaxies to stay intact, and as well as stars within a galaxy from flying apart, requires much more matter than what we can see, matter that has eluded the most advanced telescopes to date, because it does not give off or absorbs any light. And so the dark matter in the universe makes 27% of the mass energy density. The ordinary matter, the stuff that we are made of which everything else that we know and touch is made of, is only 5% of the density. The remaining 68% is in the form of dark energy, which we believe drives the accelerated expansion of this universe. And so the fact that we only know a few percent, 5% of this universe, of course, makes us humble, but I believe also determined to find out more. How can we resist not to find out more? So last spring, I visited the Death Valley National Park together with my younger daughter, Julia, and among the many beautiful things that we saw, we saw also the night sky filled with the most stars that we ever seen in our life, I believe. So I'm sure that some of you have had this amazing experience. But what we should remember is that these stars that we see in our own galaxy, and of course all the stars that we see in every other galaxy out there and cluster of galaxy in all the universe, such as in this cluster of galaxy, the Coma Cluster, which is seen in this picture of the Hubble Space Telescope in the optical. So this is just a cluster which is 300 million light years away, and it has thousands of galaxies, and each one has hundreds of billions of stars, just like our Milky Way. And so remember, we're not alone in this universe. Hubble showed us in 1924 that there are many galaxies out there, just as our Milky Way. So if we add up all these stars in all the galaxies, in all the universe, actually what we are seeing is really the tip of an iceberg. We only see 1% of the total matter in the universe. The majority of the matter, the normal matter that is out there visible to us at all wavelengths, from gamma rays, high energy gamma rays, to microwave, to radio waves, it's mostly in gas, in the diffuse gas, in dust, mostly hydrogen, helium, which fills the spaces between these galaxies and stars. So 15% only total, of which only 1 is in stars that we can admire, is the normal matter, and the remaining 85%, it's invisible to us, is in this form of dark matter which remains to be found. So if 85% of this matter in the universe is dark, you wonder how can we know it's there? So that's the question that we have. And we can measure the presence of dark matter through the gravitational influence that it has on all the visible matter, from individual galaxies to the clusters, to the larger structures. So we know how much dark matter there is there from precision cosmology, which in the past 20 years or so has given us an exquisite amount of information about the origin, composition, and evolution of the universe, right? We think the universe started with the dense, hot phase at the Big Bang and began expanding about 14 billion years ago. And just a fraction of a second after this Big Bang, we have such a fast expansion, and all the matter is created, both neutron, proton, but also the dark matter. And so after 400,000 years or so after the Big Bang, we have this universe which is hot, still, and dense, but quite smooth, as we see from the measurement of the cosmic microwave background radiation measured by Planck in that picture. This shows very tiny temperature fluctuation in the universe in all directions. And there are regions, spots, where there is more mass, and these spots got bigger and bigger because of gravity. So gravity pulled more and more matter in these regions, which became then the seed for the structure that we observe today. Without dark matter, these spots could have not become clumpier, and so we conclude, we know that dark matter is the seed for normal matter to clump and to form galaxies and structures. And I would say it's not only that dark matter is responsible for the galaxies not to fly apart, it's actually responsible for the galaxies to exist in the first place. Without dark matter, there would not be galaxies, there would not be our own Milky Way, there would not be the solar system, the Earth, so we would not be here. So it's as fundamental to our existence. We say it all the time, but we want to remember that we know of the presence of dark matter in the universe only through its gravitational pull on visible matter. And so, of course, we have to spend a few, I expected, I thought I would speak more, but it's okay. These are stuff that we see and hear all the time, but it's always good to listen to it again. So I will just go through a couple of the studies or evidence about this, about the presence of dark matter. The most convincing, or maybe easier to understand, is this study comes from the study of rotation galactic rotation curve. So stars in a galaxy rotate around the center just like the planets, and our own Earth around the sun, and the sun rotates around the Milky Way. So we can use this velocity to measure the mass of the entire Milky Way, just like we measure the mass of the sun from the motion of the Earth around it. So in the 1970, this great astronomer Vera Rubin, she died only a few years ago, and collaborator Fred Kant measured the rotation velocity of a galaxy after galaxy after galaxy. A large sample of galaxies were measured, and the rotation velocity, if you plot the rotation velocity as a function of the distance from the center of the galaxy, you would expect to see a behavior which falls down as 1 over r squared from Newton gravity. What they found was, however, both from the measurements of the visible light in stars and also from the Doppler shifted 21 centimeter light, they found that this velocity is constant, almost constant throughout the extent of the galaxy as far out as you can measure. And this fact that the velocity is constant could not be explained by the visible matter, so they invoked the presence of some additional stuff, the dark matter, about 10 times the visible matter, to explain these curves. And so that is the evidence of the presence of dark matter in a galaxy. And of course, sorry, where is it? Here. And before Rubin, of course, Zwicky studied the motion of an entire cluster of galaxies, the motion of galaxies in a cluster like the Coma that we mentioned before. And he came to the same conclusion in the sense that you need a lot more mass to explain how fast these galaxies were moving around this cluster. And he gave the first time the term of dunkel materia, dark matter. But he was not taken as serious, probably for many reasons, but he took the systematic work of Rubin and Kant to really sink into our mind that this dark matter is really out there and explains this behavior of stars in a galaxy and also galaxy in a cluster. And probably the other phenomenon that through which we can see the presence of dark matter in the universe is the phenomenon of gravitational lensing, which was, of course, postulated by Einstein in his theory of general relativity, by which light is deflected by the presence of a mass. And what is beautiful to see here in this picture is just an example of this gravity at work. So that's the bullet cluster. It's a system of two colliding. This was already several years back, I think. The observation. So these two colliding clusters where the three components, the visible light, the gas, and the dark matter behave quite differently during this collision. The stars, which are observed in optical, just don't care much about this collision. They pass right through, and you can see them at the edges. The hot gas of the two colliding clusters interact electromagnetically. The gas becomes hot, and so it emits X-rays, which is detected and seen here in pink. So in the central region, you have where most of the mass, visible or normal matter of the cluster of galaxies concentrated in X-rays from the gas. And then you have this third component, the dark matter, which is detected indirectly through the distortion of objects which are in the background. And so the lensing is strongest in these two regions, which are shown here in blue, essentially showing that, or supporting the idea that most of the mass in the cluster, which is not visible, is in dark matter, and that dark matter doesn't give a damn, doesn't care about the presence of normal matter. It passes right through from one cluster to another. So, as if baryonic matter were not even there. So these are the three evidences I wanted to tell you about, and we conclude that dark matter holds the universe together, but to this day, really, Nobody knows what it is. The fact that we haven't detected yet, or it has eluded any telescope or detector we have built so far, means that its true nature still has to be, of course, uncovered. But there are quite a few things that we have learned throughout all this cosmology and astrophysics observation. And so this is a list of the things that we know about dark matter. For sure, the first thing that we know is its abundance, and we know this number, how much dark matter there is, with very high precision to the percent level from the cosmic microwave background radiation measurements. And so every candidate that everyone can bring up must satisfy that Rayleigh abundance. We know it's cold or non-relativistic in the sense that if we moved too fast, if it were too fast, it would suppress the formation of structures. It would not allow small structures to form, and therefore we wouldn't see the universe as we observe today in large scale, at the largest scale. We know it has no charge or no self-interaction. We have seen from the bullet cluster example that it doesn't interact much with itself, only gravitationally. And then, of course, we know that it's non-baryonic because from the Big Bang nucleosynthesis and from the CMB, we can measure the amount of light elements from hydrogen to deuterium, helium-3, helium-4, and lithium-7 when the universe was very young, that 1/10 of a billion. And from these measurements, we can infer how much normal matter there is in the universe, and we know that that normal matter is only 5% of the total energy density of 1/6 of the total. So the fact that it must be stable is also clear because it should not decay. Otherwise, it should still be here today, so at least it should be long-lived with respect to the age of our universe of these 14 billion years or so. So here, when we ask if any of the standard model, when we look at the known elementary fundamental particles, here is a nice picture of the 6 quarks in the top half and the 6 leptons below and the force carriers. And as we understand it from the standard model of particle physics, and we ask if any of these fundamental particles known to us could be the dark matter, the answer is no. Therefore, we are looking for something which is beyond the standard model of particle physics, as we say, and the leading hypothesis for dark matter is that this is a new, yet uncovered, fundamental particle which was created in the early phase of the universe. And so I don't have to explain to this audience this pretty picture, but we talked about the early phase, and then we talked about the CMB and the universe as it is today with all the structures that we observe. So we're talking about a new particle, but what kind of particle? I mean, theorists, our scientists have a great fantasy, especially theorists, and so we have a zoo of particle candidate. Where is it? Proposed to explain the dark matter, and of course, these candidates span a huge range of mass. This is the mass of the particle is in electron volts, which is a unit of energy, with let's say the mass of the electron being 500,000 electron volts. So we have the mass of the particle candidate, and in this plot, the height of the column represents how many papers have been written about that candidate. And so we go from the very light axions that are quite a great candidate for dark matter, or even fuzzy dark matter with tiny, I don't know how to measure that, to primordial black holes. We have this different new type of neutrino that we're searching for, sterile neutrino. And we have this class of particles, the weakly interacting massive particle, which, of course, have received the largest attention, have been very popular, and the main reason is that particles with the characteristics of WIMPs naturally occur or are predicted in theories which extensions of the standard model, such as supersymmetry, the lightest supersymmetric particle. This neutralino can be an ideal WIMP or a Kaluza-Klein photon in extra dimensions. So we like these WIMPs. because we can see them naturally. They are theoretically, we say, well motivated, independent of solving the dark matter problem. But you can see as an experimentalist, actually, when you look at all this zoo of candidates you have, eventually you realize where you're looking. If you want to contribute to this problem, you're going to search in an area where you know you can make a contribution, namely if you can measure masses which are, let's say, at the level of a proton mass or hundreds of GeV, but not something which is 10 to the minus 20. And so I'm going to focus on WIMPs, of course, today, because it is the topic, or is at the basis of, is the principle in which the XENON experiment is based on. So we're still using 3 different approaches to search for WIMPs. We can produce them at colliders, at the Large Hadron Collider at CERN. So when 2 proton beams collide with its highest energy, we expect to reproduce actually the condition of the universe when it was this 1/10 of a billion of a second old or young or whatever. And so we expect to produce new particles at this Large Hadron Collider, and then we can see them with these beautiful cathedral detectors that are placed along the interaction points. Of course, the dark matter could be heavier than 2 TeV, and we might not see it, but that's a caveat. But more importantly, the new particles might be buried in all this background that all of us, of all the approaches, have to fight. The second approach is to look for dark matter annihilation in dense region of the sky, of the cosmos, such as in the sun or in the center of the Milky Way. And so if these particles annihilate with each other, they produce neutrinos, gamma rays, antiparticles. And so we have the Fermi telescope out there, we have the neutrino telescope in the ice of Antarctica, and we have the spectrometer on the space station looking for antimatter. So this is the indirect detection approach. And the third approach is the direct detection. We are looking to detect this WIMP or this dark matter particle in an earthbound laboratory, assuming the caveat here is that the interaction strength is not too weak for us to miss it, but that's of course something that we will find out as more experiments are made. So the direct detection is very simple principle. We measure what we care to measure. Our observable is the tiny energy, which is imparted to a nucleus if a WIMP elastically scatters off this nucleus of an atom on Earth, in a detector on Earth. And the majority of the signals that you expect in this approach are coming from electrons or photons. Background, majority of the background will make collisions with the atomic electrons, and the atomic electron collision is more at the level of a tennis ball against the wall. So the momentum that is acquired by the electron is, and the energy is deposited over a larger amount of space, whereas in the elastic collision of a WIMP with a nucleus, 2 billiard balls, you have a very confined region of space where the energy is released. And this is one way to say we have ways to discriminate this elastic collision from the majority overwhelming collisions which come from background. So when we, as an experimentalist, the first thing we ask is how much is the energy that I have to detect, so we can calculate from kinematic the energy that is imparted to the nucleus. And for most materials that we can think of to build a detector, we have energies which are in the 10th of keV, and that's the first challenge. But then we calculate the rate, and the rate, of course, is determined by the number of nuclei that we put together, but also depends on the density of dark matter in the halo of this galaxy where we are, and the velocity distribution of these particles. But it also depends on particle physics, the cross-section and the mass that particle physics tells us. And essentially, I didn't want to bother with the numbers, but what we see is that the expected differential event rate is just a falling exponential without any bumps, any features, and is simply much steeply falling for light WIMPs than for heavier WIMPs. It is an experimental challenge to look for such it is like looking for a needle in the haystack, as we say, and the reason is that if you calculate that event rate that I showed in the previous equation with the cross-section value and mass that we have studied until now, let's say probed so far, we expect to see an event rate which is less than an event or so in 1 year in 1,000 kilogram of target. So it's really a very rare interaction. Of course, the energy, as I mentioned, is small. And most importantly, the holy grail of all these experiments, like in other approaches, is to disentangle this signal from this huge background. This huge background is actually coming from a variety of sources, but to make it short, a lot is in the natural radioactivity in the materials that we use to build this detector, in the environment where we place this detector. We are radioactive. I mean, I'm very radioactive today, especially today. Sorry. The natural radioactivity from our body makes you count maybe 10 million events per day. If I would put a counter next to one of you, typical 70 kilogram persons. There's a lot of counting, a lot of radioactivity. The Earth itself is very radioactive. And the Earth is very radioactive, but it's also bombarded. And this is mostly the uranium-thorium chain, the radon. But it's also bombarded we are constantly bombarded at the surface of the Earth by cosmic rays. I mean, of course, we are bombarded by WIMPs and neutrinos, but also charged cosmic rays. This is the main reason the first requirement is to operate this detector deep below the surface of the Earth. In order to shield them. And so we use mountains, we use deep mines, and there are maybe 17 underground laboratories around the world. I work at the Gran Sasso underground laboratory in central Italy, which is located under the Corno Grande in the Apennine Mountains, about 1,400 meters of rock. Above this lab. It was excavated a long time, more than 30 years ago. It has 3 main experimental holes, which are like cathedrals again, because they are 100 meters long, 14 meters in height, and it hosts a lot of experiments in search for rare events, including the XENON family of experiments. And it is the largest laboratory worldwide. There are laboratories which are deeper, such as the Jinping lab in China. But this is a nice place to do science, and of course, it's not that, and I'm very grateful that very happy that when it was time to decide where to put this XENON project, I ended up choosing this Gran Sasso laboratory, not because I'm Italian, I'm proud to be, but just because the location. This is in a region of Italy which is a natural park, and the Abruzzo region is just beautiful, it's rich of great traditions and food and wine, by the way, which doesn't harm. But the direct access through this 10-kilometer tunnel makes it very easily accessible. And of course, the location, also the proximity to a major airport such as Fiumicino. And you put all this into account when you want to carry out a research program, since you take your flight from JFK or Newark to Rome, you rent a car, you drive 1.5 hours, and you can be at the lab, actually, and you don't have to sleep. I mean, if you can. It's getting harder and harder, but typically I go straight to the lab. So the location, these 3 points make the Gran Sasso Laboratory a great place to do the research that I do. And so in these laboratories, both at Gran Sasso and elsewhere, there are, of course, a variety of experiments in search for dark matter in the direct way, and all these experiments use different detectors and technology, from semiconductors such as germanium and silicon, super cool, these are cryogenic bolometers, to scintillating crystals, also very cold, such as the calcium tungstate used by the CREST experiment. And a large number of them use liquid noble gases, such as liquid argon with the Dark Side project and liquid xenon with the XENON project, the LZ project in this country, and also the Panda X project in China. So overall, detectors with liquid xenon have led the way for the past 10, 15 years in terms of having made the fastest and the most advanced progress compared to other technologies. So we'll spend a few time about why liquid xenon. But here is the state of the art. You might wonder, what have you seen in all this time? We haven't seen anything. We haven't detected any signal yet, unfortunately, but we have been able to constrain the WIMP nucleon interaction cross-section to the best level. This is the Xenon 1-ton result of 2018. So this shows the spin-independent WIMP nucleon normalized cross-section as a function of the WIMP mass. Of course, the solid curves are the ones, means that we have excluded all the region of interactions, cross-section and mass. And you can see with the Xenon experiment, we have excluded a large range of WIMP masses, even going to low mass to light WIMPs with the ionization signal only. And so you can see, however, that the most stringent limit, the most, when we started, it was 10 to the minus 43 or so, the cross-section of 42. So we have excluded several orders of magnitude in this parameter space. But you see Panda, Lux, Xenon. So the advancement has been made by Xenon detectors. So what is special about this Xenon? I mean, I wanted to say a few words. That the main reason that we like this material, of course I like it and I've studied for a large fraction of my career, mostly because it is a great ionizer and scintillator for radiation detection of all type. And this is the last point. You have two-signal ionization and scintillation in response to radiation. You can do a lot with these signals, especially if you, as we have done, improve the technologies to detect them efficiently, especially the light. For a long time, the scintillation light, when Alexei was standing in the audience, yes, he was my postdoc early on at Columbia, but we didn't care. We didn't dare to think of detecting the light. It was all charge readout. We didn't even know how to detect the light. We would use actually light sensitive, visible phototube, but coupled with the wavelength shifter. There were no photomultiplier at that time sensitive to this very deep VUV light of xenon. But for dark matter, what's important is that it is a large nucleus with all these neutrons and protons, which is good for spin-independent coupling, since that probability goes with the square of the number of nucleons, right? But you also have, you don't forget that xenon natural has a lot of isotopes with spin. So if the WIMP like to couple to the nuclear spin, we can give him a lot of nice isotopes directly in the same detector, which is not bad. It is, for dark matter, the scalability of a target has been, of course, a driving motivation, because you want to have as many target nuclei in order to probe this very rare phenomenon. So the fact that it's dense, 3 times the density of water at minus 100 degrees Celsius, when we liquefy it and make it cold, that's the density. And with a Z of 54, xenon is a very good absorber for penetrating radiation. So, and when you think about minus 100 degrees C, is sometimes I say it's an easy cryogenics. On the other hand, we have learned over the past many years and with many years of R&D to how to liquefy and especially keep cold and stable these big targets of thousands of kilograms over not days, not months, but years of running time. Because being a rare event, you want to put a large target mass together, but you also want to count, let's say, or wait for this damn WIMP to come over many years. So being able to operate a cryogenic detector over a long period is very important. And we have improved these technologies a lot. No intrinsic radioactivities other than krypton-85. That's an important consideration. We will see today these experiments that are advancing, have advanced the most, are phasing the ultimate concern in terms of background, which comes not even from krypton, but from radon, which is everywhere, and so we are fighting the intrinsic radon, which is, of course, in the liquid, which comes from everywhere, from mostly surfaces. But in terms of xenon itself, since it's a noble gas extracted from the air, it contains tiny traces of krypton as well. Krypton wouldn't bother us, but krypton has a radioactive isotopes, which would bother us. And we have learned how to remove krypton through cryogenic distillation. That has been a major accomplishment of the XENON program. And when I say it's a noble gas, another concern that we have is, of course, the cost of this target. And since it's a noble gas, it's actually obtained through distillation of air as a byproduct of the air distillation. And the cost of xenon over the 20 years that I've used it really fluctuates with the market. We should make a very nice model here because it's a great way to make money. Because oxygen is needed to make steel, and steel is needed when you build bridges, when the economy is strong. And so when there is a lot of oxygen production, the cost of the xenon byproduct is low. And it can be as low as $2-3 per liter of gas, but today, for instance, it's as high as $20-25 a liter of gas. It really fluctuates with the economy. And this is a huge difference from $3 to $25 when you think that you need 500 liters of gas to make 1 liter of liquid, of 3 kilograms. So on average, you're talking about $20-25 per kilogram. So if you have a 10-ton detector, the impact of the cost of the xenon itself on the total experimental cost is not small. Not to mention that with such a price for the target, you have to be extremely careful, or let's say, in designing a cryogenic and recovery system, which doesn't, because as easily as you get it from the air, you can easily give it back to the air with a small mistake, and then you lose $20 million. But most importantly, even if somebody gives me $20 million, I cannot buy 10 tons of xenon within a day or 2 or 3 because the mass production worldwide is limited. So just a few words, I couldn't resist, but anyway, that's the xenon. But this is the reason why xenon is exciting, at least for me, because of these complex processes, which, however, give us these signals. So whenever you have a particle, you are going to excite the xenon atoms and molecules and form these excited states, excited molecules or dimers, which go to the ground state with the emission of VUV light, 175 nanometers scintillation photons. But you also have, of course, ionization electrons produced, and if you can apply an electric field and overcome the recombination and keep these electrons free, you're going to have free carriers. And recombination itself actually leads also to the formation of these excited states. So the source of light in xenon is actually both from direct excitation and from recombination. And then you have the charges. Most of the energy goes into the vibration of this medium and in heat, which we don't detect yet. But the charge and the light are the two signals that we detect. And what we have done over this year is to use the xenon in liquid form in a so-called time projection chamber, such as shown here, operated in 2 phases. So the type of detector which is at the basis of all these experiments searching for WIMPs is a 2-phase TPC in which you have a container filled with this highly purified and liquefied homogeneous stuff, which is liquid xenon. And when you have a particle interaction, you are going to have the direct scintillation light, which is few nanoseconds fast, very fast. And then you're going to see the delayed ionization electrons. But the trick that we used is not to detect the electrons directly. We drift them across the liquid layer by the application of an external field. And when they reach the liquid to the gas interface, we accelerate them in the gas. And as they accelerate in the gas, they emit scintillation light again in the same wavelength. So we equip the cylinder in which the liquid is contained with these photosensors, this special photomultiplier sensitive to this wavelength, to detect both the S1 and the S2, the direct scintillation and the secondary scintillation, which is proportional to the energy deposited. And we have an amazing 3D imaging detector because the Z, the drift time, the drift of the electron across the liquid, if we can make it and keep it clean so that they can drift freely, will give us the Z coordinate where the interaction happens. And the pattern of light on this top and bottom array, especially the top, gives us the XY coordinates of the event. So it's an amazing power to have a 3D imaging for each event, if you like, because you can, as we say, fiducialize the volume. You can select only a central region of your detector where the background is lowest, because most of the background from material radioactivity is concentrated around the edges. But it also allows you one thing, which is, as we make this experiment large, is very important, namely to recognize the multiplicity of the events, because a WIMP event will only give you one scatter. It's a single scatter event, whereas a neutron, which is the enemy of the WIMP in the sense that it gives you a similar response, the neutron with its mean-free path, it's such that it loses energy in multiple points. And if you have a detector which can recognize multiple site interaction from single site, you can have an additional handle to reject neutron background, which is, of course, the ultimate background that we have in terms of nuclear recoils of the type the WIMP creates. A lot to say here, but also the detection of both simultaneously charge and light is also giving us a discrimination power, because the ratio of these two signals depends on the type of particle that we're dealing with. So it's very different for a WIMP recoil than from an electronic recoil from background, and we take advantage of that. But it's mostly the self-shielding of liquid xenon. I said it's very dense, and at 0.54, a few centimeters of xenon at the edge is enough to suppress a lot of the background which comes in from the walls. Self-shielding, fiducialization through 3D imaging, the possibility to detect single from multiple events, and of course, the ratio of the two signals as a discriminating factor as well, and much more. I mean, anyway, this is the principle of operation of the time projection chamber, which was realized in this family of detectors of the XENON program, which started in 2005 with its first prototype, Xenon 10. As I mentioned at that time, the result of Xenon 10, only after 5-6 months of data, probed a cross-section of 10 to the minus 43 or so square centimeter. And today we are at the 10 to the minus, we are taking data as we speak with this last baby of the family here, Xenon Anton, the largest, with 8,500 kilograms of xenon in it, with which we want to reach, after, let's say, 4 years or so of data taking, 10 to the minus 48 square centimeter. Of course, more than that, I wish that we can see something in this last machine. But we realized the first ton scale experiment, Xenon 1 ton, which has given a lot of results. And of course, we look forward to eventually, ultimately build a 50-ton scale detector with liquid xenon to probe down to the 10 to the minus 49 square centimeter, which is where the neutrino fog or floor is, in terms of where the neutrinos from the sun, from the atmosphere, hopefully from a supernova, actually gives us plenty of signal. So that's the plan. That's the family of xenon detectors. So if you were to visit the Gran Sasso laboratory, and I welcome every one of you, that's what you would see, the infrastructure that we had to build for the Xenon 1 ton experiment. And so what you see is a 3-story tall building, and you notice that it's not that it has no doors or no windows or whatever. I pushed to have it with transparent walls so that people could see the beautiful equipment and systems that we built to operate this experiment. So now it has become the highlight of the lab. Every show, every visit, the president of the the president of Italy, who else, all the famous luminaries, they're brought always in front of the XENON building because it is indeed beautiful. And so the building contains all the system that we need to operate the detector, which is at the center of this 10-meter diameter, 10-meter tall water tank filled with demineralized water, but also viewed by photomultiplier on these internal surfaces. So it works as an active muon Cherenkov Vito detector. So the TPC itself, the detector, is in the middle through this umbilical cord, which is this very long, of course, all this insulated pipe which carries the liquid in and out of the detector. That's just to give you an idea, this is the detector. This is XENON 1 ton, actually, a few years ago. It took a couple of years to assemble, to build it, and many years of R&D. This is the first time projection chamber with 3,300 or so kilogram of xenon. Was a step that going from the 100 kilogram scale to the 1,000 kilogram scale was quite impressive and scary, but we solved a lot of the challenges that this demands. You see a lot of copper used for field shaping. You see a lot of white stuff, which is Teflon. PTFE is a very good insulator, but it's also a very good VUV reflector, since we are trying to detect VUV photons. The arrays of photomultiplier, you can see the bottom array more clearly. So that was in the clean room above ground, just before bringing XENON 1 ton TPC underground and mounted in its cryostat. And something I forgot to say is that when we built this detector, a lot of the years of prior to assemble, or actually realizing all the parts, all the screws and nuts, went into careful screening and selection of materials in order to choose only the copper, the PTFE, the steel, and everything else with the lowest traces of radioactivity, of intrinsic radioactivity. And the same went for the cryostat. Of course, this detector is inside. This is now mounted underground under the dome of the cryostat, and you can notice that so of course this detector gets close into an inner vessel. It's insulated with a dual wall vacuum cryostat, we say. That's the inner dome and the outer dome. You can see the outer dome is larger than what you would need. And that's because I had the vision that after XENON 1 ton, we could easily swap the detector with a larger size using the same outer vessel, which is essentially what we have done last year. These are the arrays of photomultiplier, and of course you need this vessel. And of course I have to show, where am I here, to give you the idea of the size, because at the time of XENON 1 ton, I spent quite more than a year at Gran Sasso as technical coordinator. So again, designing and finding the stainless steel, which was the lowest activity steel. You call companies after company, and you screen plates and plates of steel until you can settle on the lowest radioactivity one. And that's to keep the size of the vessel, which was built by a company near Vicenza, I remember. Yeah, it was a fun time, but that is the XENON vessel. And then this thing is mounted, as I mentioned before, inside a water shield, because even at Gran Sasso, we still have a residual flux of cosmic rays, so it's never enough, the depth. So we shield this detector, the umbilical pipe, and the cryostat is hanging. That was the most amazing phase of my life, to see that mounted inside this water tank. And so we have this detector sitting in the center of this tank, which then we fill with water after we instrumented with the phototube and the reflector on the walls. This is a nice picture which was taken to show the muon Vito detector of XENON 1 ton. And I think this is, I'm taking too much time. Some of you might know that the physics results of XENON 1 ton are quite some. It's not just the spin independent. The 1 ton year exposure that we released, we amassed the largest exposure actually in the business. with the exception of DAM, I would say maybe. And so despite this large exposure, we didn't find any WIMP, as I told you, but we could probe a lot of other interactions of dark matter particles, from light dark matter to bosonic like dark matter. As I will tell you more tomorrow, maybe in the other seminar, we are excited to search for, let's say, solar actions, and we have neutrino magnetic moment possibility, but especially with my group, probing the coherent scattering of solar, boron, and neutrino on xenon nuclei was also exciting, and so on and so forth. So a lot of papers from this experiment. But right now, our focus is on this new guy, the xenon Anton, which is actually happening, as I mentioned. Despite COVID, last year there was an intense year thanks to the dedication of many people, the few people that we had on site. We managed to keep going and build this new detector, which has now 8,500 kilograms of xenon, and the new liquid xenon purification system that especially my group has contributed, and an active neutron beater inside the water Cherenkov, and also a new radon distillation column to fight the ultimate enemy on the point of electronic recoils due to radon. But the idea, I showed you briefly the size of the dome, was to reuse most of the infrastructure of xenon 1 ton and subsystem, and adding this 4 new system, which is not trivial, but we have done it. And in fact, I will just show you a picture, because last year, around March, just before COVID blocked us from everything, we managed to bring the detector underground. And this is still inside the clean room, and then we managed to move it underground. Here is the clean room inside the water tank, actually. And this is it happened just a few days before the lab was officially, let's say, closed because of COVID. So we managed to install it. It's a beautiful detector. It's larger now. One of the challenges for some of you who know these technologies, that from xenon 10, which had 15 centimeters of drift for the charges, xenon Anton has 1.5 meters of drift in a TPC. So it is quite challenging to keep these free electrons free from being eaten. And the reason why it's so important is because a 10 keV energy nuclear recoil from a WIMP or for whatever, 10 keV nuclear recoil in liquid xenon corresponds to a handful of charges. So there is no charge-sensitive amplifier that I know that can sense this very tiny amount of electrons, and that's the reason we use the trick of the dual phase. We turn these electrons into light, but still, if we lose a few of them, it's not going to be good. So keeping the liquid clean from especially electronegative impurities such as oxygen and water is the first requirement for such a detector. And then you remove radioactivity such as krypton and radon. But first you have to keep it clean, you have to keep it cold. So, and this is, in fact, I'm ahead of my time, and so that's, sorry, maybe I should wrap it up. This is the cryogenic plants that we had to develop for xenon 1 ton, because it was the first time we were handling thousands of kilograms of xenon compared to my work with xenon 10 and xenon 100. So there is a cryogenic system, which is based on all the R&D time mostly at Nevis Lab at Columbia. But also we designed a special bottle. You can imagine that there are about 2 million of liters of gas to make 8,000 kilograms or so. So all these bottles, you cannot handle a room of bottles. So we designed a special bottle, let's say, to store and recover this precious material, the restock here. But we also have a purification system, and we have a radon cryogenic distillation. Sorry, not radon. This is the krypton cryogenic distillation over there. Anyway, these are just some photos. The blue is the Columbia blue. That shows because we built it. And this is the sphere that I'm very proud of because I followed very closely. In fact, it's me on top of the sphere. And this is the main guy who helped me with this cryogenic system and my students there. Of course, this is underground. The same cryogenic system is being used for xenon Anton. It has 2 cryogenic, 2 pulse tube refrigerator, which have enough cooling power for also the 9-ton detector. So these are just pictures, and this is the latest addition, the liquid xenon purification system. This is now cleaning the xenon in liquid phase, and we have achieved more than 20 milliseconds. For those of you who know what that means, electron lifetime, meaning that we have achieved the very the highest purity in a liquid xenon TPC that I've ever dreamt of. I mean, for a long time we have been fighting to get millisecond, and now we're talking like nothing at every telecom, and we have 16 milliseconds, as if you were normal. But anyway, and so the liquid xenon started to flow through our vein as we treated last year. I was a Gran Sasso despite COVID. That's where the Italian passport turned to be very useful last year, because I couldn't travel, but I could travel with the Italian passport, and of course quarantined. I had to spend 2 weeks in our apartment that we rent over there. But I was there because we pushed to start filling the detector, and that started around September 1st of 2020, and then I came back. So, and here is the other system, this neutron veto, which will use gadolinium-loaded water, the same water, but we will load it with salt of gadolinium in order to have a very effective and efficient neutron detector, neutron veto detector. So I guess few words about this. Of course, when I say we, of course I'm not doing this alone anymore. And so that's the collaboration. By now we're about 180 people from 27 institutions around the world. And I guess what I want to say is the enthusiasm and the commitment of this more than 100, I guess about 100, between master students in Europe or PhD students and young postdocs that work on XENON. It is their enthusiasm and commitment that push me every day to fight every obstacle that we encounter in order to get there. So in fact, several of my own students have gone off and become PIs at some other collaborating institution around XENON, or maybe have joined a competing experiment. No matter if it is a collaborator or a member of a competing experiment, whoever has spent time in the XENON family will always be, of course, in my heart, and I'm thankful to this collaboration to follow my dream. And so I stop here, sorry for taking too long. We continue to search. We are excited that the search with XENON and TON started. As I said, we're taking data, and yeah, we hopefully will contribute to answer some of these fundamental questions. And nobody knows if it's just the wind, but we continue to search. Thank you.
Thank you very much. Thank you for a wonderful lecture. Are there any questions or comments? Jack.
Yes, hello. I would like to ask, is there any cosmological evidence that WIMPs act other than only gravitational? Because if they would interact only gravitational, it would probably be very hard to detect them.
Right, I think I said that there is no evidence other than gravitational interaction.
But to detect them, do you need other interactions than gravitational?
Say again?
To detect WIMPs, do you need
you need them to have other than gravitation. So we expect for WIMPs, at least the word says weakly interact. So we expect them to have some weak interaction with normal matter. Weakly interacting, that's what we expect. Of course, in addition to gravitation, that they interact through the weak force with the normal matter, such as the xenon on my detector, right? Yeah. That's one of the assumptions we made, yes.
Okay, let's say after all the experiments that you do years from now, whatever, and you detect nothing, what does that mean?
Why do I get asked always the same question? What does that mean? First of all, it means that I had a lot of fun in my career, and I'm still very happy. Because one of the reasons I'm doing that is because it's still fun to keep pushing yourself and your technology, which gets used by others. I mean, you know, the competition has been amazing, and we keep driving each other. So of course, I'll be happy than that, but yeah, I will be sad. But it's not actually too much, there's not much to be said. Of course, I want to make a discovery, I want to see a signal. But as we often say, seeing nothing will mean a lot, because it means that at some point, many of us will have really to seriously start thinking in another direction. We have to put, for instance, this WIMP miracle to rest. If we stop now, we always wonder, oh, maybe he was just hiding there at 10 to the minus 47, minus 48. So if you have the ability to search this little painful last few orders of magnitude before neutrinos swamp you with their signal, it's worth doing. Because it will change our view, and we start looking, we already, of course, the fact that no WIMPs or no supersymmetric particle was found in the past 4, 5 or more years have already enhanced our efforts in different directions. We are looking in every other direction. Axion searches are very strong. We're looking for sterile neutrino. We're looking for light in the dark sector, the accelerator. We're looking everywhere, and we should. I will keep looking with this because that's what I can do best, and I think we were able, actually I'm amazed that we were able to get to the 10-ton scale or 8, 9 ton of liquid xenon. It was not in the XENON proposal that I submitted to the NSF. The XENON proposal was for a ton scale. I thought I would discover it in 4 or 5 years. It was for a ton scale detector, which we did already in 2016 or 17. But so, yeah.
I have a question about the, you mentioned the height of the cylinder, the volume of the xenon. In recombination, I was curious, is there any meaningful limitation to how far or how big you can make the cylinder without losing too many electrons to recombination?
Well, there's going to be a practical detector limit, because then the dead time, as you go, these are slow detectors, right? The drift time is still quite slow. If you make them extremely long, it takes already milliseconds now to drift. So it becomes an issue more of electronics readout as well. They become it slow, because you're still looking for the charge. You drift them across the 1.5 meter. The next generation detector, what we talk about, the 50-ton Darwin type detector, will have 2.5 meter, 2.6, and the challenge is already quite large. But in principle, no. I mean, if you were happy with a slow response detector, which we can't afford.
I'm making a lot of exercise today.
So at one point you mentioned elastic scattering off of the nucleons, but then when you talked about the reaction with the xenon, it was an absorption and things being emitted. I didn't quite understand, what was the role of the elastic scattering?
The direct detection primarily is the elastic scattering. We assume that this WIMP makes a scatter which is elastic with a proton or a neutron in the nucleus of an atom of xenon, elastically. And so it's like 2 billion ball, because the mass, suppose the WIMP is 100 GeV or so, a similar mass, two similar sized balls. What I mentioned is that in the elastic scattering, yes, the nucleus, overall the nucleus itself will move very little. It gets a very tiny amount of energy. We can calculate that energy in an elastic collision of 2 balls, and it is maybe 10, 20, 30 keV of energy which is imparted to this nucleus. So it is an elastic collision that we first look when we look for nuclear recoil. When we say the energy deposited by the WIMP into a nuclear recoil energy, that's our observable. Yeah, exactly. Okay.
Any further question or comment? Well, if not, let's thank our speaker for a great lecture.